Hi, everybody, and welcome to this episode of American Scientists Google Hangouts. Today, we're very excited to have some of the authors of our latest cover story with us to talk about some of their research. I'm Sandra. I'm the managing editor of the magazine. And today, we have with us Indrek Wichman, who is a professor at Michigan State University. Hi, Indrek.
Hello.
We also have Sandra Olson, who is a researcher at NASA Glenn Research Center. Hi, Sandra.
Hello.
And we are also joined by Fletcher Miller, who is a researcher at San Diego State University.
Hello.
Okay, so we are going to be talking today generally about sort of fire research in microgravity, as well as some specific topics covered in this cover article. We were really excited to have some cover art that Sandra provided for us. So I'm going to try to hold that up, see if we can see it. So lovely image there of some of the fire research that everybody does. So one of the things I wanted to start out with, maybe Sandra, you could take this one and others could chime in. First of all, let's talk about why one would want to even look at fire in space to begin with. Is there particular implications for fire safety on spacecraft?
There are. Fire in space is one of the main concerns that the astronauts have. In addition to the decompression, an asteroid or a micrometeoroid impact, or a toxic spill. So they do a lot of training to, learn to respond to fires in case they have them. The Mir space station had a couple of fires, and one of them was really bad. Was caused by a failure in an oxygen candle, which was an exothermic runaway reaction, and it got out of its housing and was like a blowtorch blowing across the vehicle. So it was a very bad fire. So we have had incidents where there were fires in space. Clearly we haven't on the space station, and that's good, but we do always have to be cognizant that there is this problem. One of the first things that the astronauts do if there's a fire alarm is they shut off the ventilation system, because our research has shown that if you have an airflow, the flames really like the airflow because you're just feeding the fire. So the first thing they do is shut off the airflow so they stop feeding oxygen to the fire.
Right.
Materials are screened very carefully so that we don't fly materials that are highly flammable. But there are always some things that are flammable that you just don't have a substitute for, and in that case, you have to just take precautions and do very careful storage of these items when they're not being used.
Right, okay. I don't know if any of the other two of you want to talk a little bit more about some of the implications here, or should we go on to the next question?
I think Sandy covered the implications just fine.
Great.
They've been the mantra for a long time at NASA.
Mm-hmm. So just one other thing I wanted to follow up, though, about Sandy is, obviously the astronauts are not having campouts in space. So these flames that are happening in space, are they particularly for any particular use, or is this just a case where you can kind of get spontaneous combustion if there's a wire fault or something like that?
Yeah, well, the cover picture is clearly a controlled experiment, and it is very carefully monitored, and we work with the crew to do those experiments. But if there's an accidental fire, it's usually due to an overheat, some component in the electronics fails. That kind of thing is what they're most concerned about caused the fire.
Mm-hmm. That makes sense. So, Indrek, maybe you could talk a little bit more about some of the history here. You had mentioned some of this in the article about some of the history of fire research in space and some of the surprising things that were found there, even sort of in the beginning of this field back in the 1980s.
Sure. Well, back in the 1980s, I don't know that there was that much being done on zero gravity work, but I think that started, Sandy, wasn't that in the late 80s maybe? Mid to late 80s. I think NASA was doing a lot of work, but it wasn't until the early 90s that I think NASA opened up the work, for academics, for people like me to get contracts and grants and to research this kind of a thing.
Yeah, the program snowballed a lot in the 90s. It started small and it grew.
and it grew huge very fast. But fire research, fire and flame research, that didn't really start, I would say, probably until the late 50s, maybe middle 60s. And there was John Derris, and there was Howard Baum, and there were a number of people at various places that started looking at fire spread as a kind of a field of research. It really hadn't been before then.
You're talking about fire here in general, not necessarily microgravity.
Fire in general, right. And that involved people, again, there were several people, several groups. Maybe a little bit before that, they had looked at these kinds of problems in propellants, so defense-related research. But that's always been, not an area that perhaps that lately the focus of fire research has been on. But that's still not an applicable area. But it's been a sort of a pretty active field of research for quite a while now. And again, it really ballooned in the early 90s at NASA.
Yeah, I would say the first microgravity work that NASA was involved in studying flammability occurred because of the Apollo 1 fire that happened in the later 60s. And because of that, we built our large drop tower here, which is a 5.18 second drop tower. And so it really built up that program because they realized this is a major issue that they need to carefully address.
Right, okay. So Fletcher, maybe you could jump in here, and I wonder if you could give us a little background on sort of the general dynamics of flame and why it changes in microgravity.
Sure. So what we're studying here as part of this project is how flames spread in microgravity, in particular once they're ignited, how fast they'll spread. And other groups are studying how you would detect those flames and how you would put them out. But the biggest difference is that in the absence of gravity, you don't have any buoyancy. So buoyancy is the tendency of hot air to rise. And of course, in microgravity, there's no up or down, so that the flame generally will form sort of like a sphere around the area that's burning, depending on its shape. So I think in this background, the Sandy actually, you can see a candle. Maybe she can speak so we can get it. You can see a candle both in normal gravity on my left at least, and microgravity on the right. And you see this little blue semi-sphere, I guess. And Indrek has a real match there.
Real life match.
Excellent. Indrek, can you show us that in microgravity now?
I can show it to you in microgravity. It's got a nice, what they call a teardrop shape, caused by gravity again. And if I turn it this way, then you see the flame has adapted itself to go, again, vertical. Mm-hmm. Pretty soon I'm going to burn my fingers, so I'm going to put it out.
Don't do that.
So in the absence of that buoyancy, the flames look very different, but that also means they burn very differently. Different products, combustion products, are produced differently, and so smoke detectors that work on Earth may not work well in space. They're set up maybe to detect certain size soot particles, and those soot particles are vastly different sizes and morphology, shapes, and so forth when you get to space. So detection of the fires is different, and how fast they spread is different, and combustion products and so forth. And sometimes maybe the detectors are set up to look at certain wavelengths of light, different colors, let's say, and if you're looking for yellow flames and the flame is blue, you might not detect it well. So there's some, visually there's differences, obvious ones, but there's also chemical differences and so forth.
Right, and so one of the things that you're kind of touching on there, you're saying they burn differently in space, but is the way that the fuel sort of aerosolizes different in space as well without the effects of gravity?
Well, sure. So the flow, really what it comes down to is what we call the effect of the flow field on the flame. So the flow is upward in normal gravity, as Indrek demonstrated. It produces this teardrop shape, and that shape, that flow, affects how much fuel vapor is coming off the surface, and it's the fuel vapor that's burning. And so if you change the flow, then you change dramatically the flame and the chemistry as well. So.
Right.
One of the things we noticed when we were burning some of the things in space is because the flow velocities we were testing are a lot weaker than they are in 1G. The fuel vapor effects on the flame shape were much more dramatic, because when the fuel burns, it creates these little bubbles and they rupture at the surface, and they let off a little jet of gas. And so the flame looked a lot more, as the cover picture shows, the back end of that flame is all contorted
flashy,
because of the vapor jet. Yeah. And so that's because of the different relative velocities. The vapor jet velocities are high enough that they really distort the flame. In 1G, that's all washed away.
So the vapor jet velocities are high enough because the airflow velocities are low enough. And so they're all comparable, and so therefore you can see the effects of both. And if you were to look at Sandy's, the cover picture, Sandy's cover picture that we took from that experiment in real time, like a movie, it almost looks like there's a little captive in there, punching the flame once in a while. And so it goes out on this side, then it goes out on the other side. So it's the old, almost like a guy in a paper bag trying to punch his way out. And it's really pretty fantastic to see that, slow-mo. Because again, it looks like you've got a little captive in there who's trying to get out. It's almost, like a comedy in a way. So the flame really does, and it goes out in various places. And Sandy, correct me if I'm wrong, but the flame has never broken apart. I mean, it's so far been strong enough that it stays intact. So a little bulge goes out and then goes back, and so on and so forth. It doesn't ever break open, does it?
It was funny because Don Pettit, one of the astronauts who ran the BAS-1 experiments, he commented that he could see little holes in the flame due to the vapor jetting. And those were the stronger tests we were doing with just air ambience. And so the vapor jetting was even stronger than a lot of the later tests at lower oxygen that we did. And he said, it's a little vortex that's coming out, and it's tearing the flame locally. So you were getting little holes in the flame.
Yeah, it's called a
and Don, who's a chemical engineer, PhD, noticed this.
Yeah.
He was really right on top of this. He loved that experiment.
Yeah, well, it is really cool looking when you see it on a film.
I should mention that Sandra has provided us with a couple of videos and some stills, and we're going to put together a slideshow so people can come back and look at that on our website. Not too long from now, we'll post about it as soon as we get it up. So thank you for that, Sandra. But Sandra, I also wondered if you could go back and kind of fill us in just a little bit here on the missions where you've been the principal investigator or co-principal or co-investigator on the BAS-1 and 2 missions. Can you describe those missions and where they took place and what they covered?
Sure. We have a very small flow duct up on the space station, and it's we put it inside the microgravity science glove box, which is an enclosure that contains the flame so that nothing gets out and nothing gets burned that we don't intend to burn. But it lets us have a test section where we can burn things in a controlled velocity. And the BAS-1 was all done in air. BAS-2, we found that we could actually vary the oxygen by diluting the ambient inside that glove box working volume. And that worked out and gave us a whole other variable to pursue. So that we've had a number of, it's been, I think, 2 or 3 years we've been operating BAS up there on and off. We'll have a series of experiments, and then we'll be off analyzing the data for a while, and then we'll come back in. But it was wonderful. The crew, it's very interactive with the crew, and so the crew is hands-on. They're basically running the experiments, and we're kind of watching over their shoulder and, indicating when we want them to change the velocity or take pictures and things like that. But it was really a lot of fun. The crew enjoys setting fires in space in a controlled way because it's very dynamic and it's really interesting to watch for them. And, of course, we get a lot of really good science out of it. So it's been a really good. It was interesting. It was used originally for a number of a couple of different experiments. So we've been reusing the same hardware to do different science, and so it's been very economic to run these experiments as well. Because we could just modify a few things and get a whole new set of experimental data. So it's been great.
So Fletcher, you were involved with the BAS experiments as well. Do you want to talk about what you were specifically studying during those missions?
Sure. So there's a number of, I think, 5 different investigators in the BAS tests, of which we're one. and Indrek and Sandra are investigators along with me on this project. And we're looking at how flames spread across thicker, flat samples. So the cover picture showed a cylindrical rod, and that's a different experiment. So are there these thicker, flat samples that represent the size of sample that NASA will test materials before they're allowed into space? Actually, the ones in BASS were smaller, but BASS is sort of a precursor experiment to an actual longer-term flight experiment in which we'll test the full-size sample. So we're interested in understanding this flame spread on thick fuel in microgravity because it's so difficult to get data in this what we call a regime. And the reason is in the drop towers you can ignite very thin fuel, thin plastic films or thin paper, and you can get basically 5 seconds of burning, and that's enough for these thin fuels. But for the thicker fuels, you need maybe half a minute to a minute even to ignite them, and then they spread very slowly. So they represent a fire hazard on the space station in the sense that structural elements are made of thicker materials, but the only place you can really test them is in microgravity. And so what we want to do is get enough of a database on thick fuels from both the BASS experiments and the future Sophie experiments that then we can maybe modify how NASA tests the thick fuels on the ground as part of a material characterization test. They have a test, NASA Standard 6001 Test 1, and that's a lot of vernacular, sorry, but they basically burn thicker fuels of different materials before they allow them to be used on spacecraft. And that's, unfortunately, that test that's done is done in normal gravity, and so the question is how representative is it of microgravity? And so that's one of the key questions we're trying to answer.
Right, okay. Sandy, did you want to add to that? I'm sorry.
Oh, I just was going to talk a little bit about the 5 different investigations that were part of BASS.
Please do, yeah.
BASS is, as Fletcher said, is a precursor experiment for the Sophie experiment, which is going to be flying around 2019. So we've got a lot of data to analyze before that, but we're planning to do much larger samples and things. But there are 5 investigations. My experiments were the rod experiments, which is the cover picture. Fletcher, as he indicated, we're collaborating on thick slabs of material. We also have an investigator, also at San Diego State, who's looking at thin films of plastic material. We have a professor at Case Western Reserve University in Cleveland who is studying spheres. And then lastly, we have an investigator at Berkeley who is looking at rods as well, but with the flow in the opposite direction. So I do concurrent flow, which is where the flame and the flow are in the same direction, which is what your cover picture is. And the Berkeley PI is looking at where the flame is going opposite to the wind. And the physics are completely different in those 2 cases. You would think they'd be similar, but they're very different. So we're learning a lot from the BASS, this precursor experiment, and it's been really, really great.
Do you think you could dig into that a little bit more? I'm sorry, Indrek, did you want to say something?
I wanted just to, Sandy, could you just say what Sophie is? I think that's an acronym, and it might be, that might be illustrative. Just
well,
say.
so's BASS, but yes, Sophie stands for Solid Fuel Ignition and Extinction. We at NASA love our acronyms, and so we try to make them somewhat pronounceable. And in that case, it's a nice name, so we call our experiment Sophie, but it does stand for Solid Fuel Ignition and Extinction. So.
Right. I just wondered if you could dig into a little bit more about the reason why the concurrent flow and the opposing flow changed the physics so much.
Well, in the concurrent flow, which is the cover picture, the flame at the stagnation region at the tip of the rod, where it's burning at the tip, that has the highest heat flux, and that's right where the fuel and the oxidizer are meeting. And so it's a very happy flame there. In the opposed flow geometry, the flame is kind of trying to wrap around. You know, you've got the rod ahead of it, and the flow is coming down the rod, and the flame is looking at the flow, you know, coming at it. And it's got to wrap itself around the rod, and it can't really close around the front until it gets to the end of the rod. So it has a harder time heating the rod because it doesn't have as good a coverage. It's not as close to the rod in that location. And the fuel vapor mixing is very different because it has to vaporize the fuel and then react it in an annular shape. Whereas in the stagnation region, it's just, you've got a nice sort of almost, it's not planar, but it's there's a similarity to a planar flame in that location. So it's very different.
Right, okay.
But I think, can I follow up with that a little bit? Not in the form of explanation, but Sandy, is it possible, I mean, somebody may be looking at it and thinking about it might say, well, maybe in microgravity, the burned products might go over the surface that's up above and somehow keep that surface from burning. Is that something that could happen in the concurrent type of flame spread?
You could say that it's washed down with the products, right, but they're also heating the rod because they're hot products. So you have an enhanced heat transfer there as well. So it's a little bit of both.
There's several trade-offs there that work either with one another or slightly in opposition to one another, but generally the concurrent spread is a little bit more fast and a little bit more intense, I think. Would that be a fair assessment?
Well, based on the data we've got so far, it seems to be that would be true in microgravity.
Mm-hmm. So, Indrek, if you want to kind of pick up from there, the flow direction is actually pretty important in the research that you're doing as well. I wondered if you could talk about what you were covering in this article regarding flamelets and what those are and how they can affect fire safety in space as well.
Well, that's a very good question. The flamelets, the research now, just to back it up a little bit, the research here deals with thin fuels. All of the research in this article was about thin fuels. And as Fletcher was saying before, the physics of the thin fuel problem really is quite different from the thick fuel problem. But one of the really neat things that we saw happen was that as you reduce the airflow into the flame, which used to be two-dimensional because the airflow was ample and there was plenty of oxygen for it, so it was almost like a front of, let's call them as little soldiers that are advancing over the surface. But as that airflow became less and less, the flame had to change its morphology, and instead of being just an advancing single front, just turned itself into a series of little three-dimensional flamelets, that we called it, that then had to advance separately. And the more you squeeze down the oxygen, the further apart actually these flamelets had to drift in order that they'd have enough, so to speak, to live on. So it's very interesting, but there's almost like a kind of a life cycle type analogy. We think of it in terms of survival and flame survival. And in order to survive, quote unquote, the flame had to change its morphology. When you say this kind of a thing to a mathematician, they really raise their eyebrow. They don't like these kinds of humanistic terms impinging on the structure of equations, right? So they get a little sketchy when it comes to that. But it's a very good way of looking at it and thinking about it. And so some of the terminology that comes over from biology we found is quite relevant to what we were doing. And that one article that we wrote in '06 did talk about these in terms of population models. So you have these populations of flamelets, and they actually have a statistical kind of a behavior, and they actually have a physical kind of a behavior. It's a very, very interesting problem.
So basically what's happening here, though, is you're kind of starving the flame of oxygen, and that's when it's breaking up into these flamelets. But there's a gravity connection here as well. This isn't a behavior that necessarily happens here on Earth. It's specific to microgravity?
Well, I mean, I think you can do this on Earth, too, if the conditions are right. And the conditions would be right if you could suppress buoyancy. And so that's the whole thought behind this device we're trying to make on Earth, the narrow channel, in which you try to suppress buoyancy so that you can simulate the action of these flamelets in zero gravity or microgravity.
Mm-hmm. But where this you were saying in the article the first time that these were discovered was actually during one of the space missions, is that correct?
I believe so. I have to say Sandy and Fletcher could probably say a lot more to that than I can, but I believe that you got in there right at the very beginning, and the American and the Russian astronauts / cosmonauts were looking at these flammability issues, and either they found these accidentally, or there was again a sort of kind of a flammability test that led to the observation that, wow, look at this. And
Yeah, we had an experiment. I was working with a fellow at NIST at the time, Takashi Kashiwagi, and we were studying a smoldering piece of paper in a very low velocity airflow, and we expected to have a circular front develop from this, or a semicircular front. And as Indrek said, we expected a uniform front, and we were just looking at, to measure the spread rate and things like that. And then what happened is the thing broke up into all these little smolder spots that were akin to the flamelets Indrek's talking about. And I just remember sitting there baffled by what was going on, and the crew up on the running the experiment was like, "Oh, that's an interesting pattern," and they were commenting on it. And I just remember Jim Tien, who was also there working on a different experiment as a combustion expert as well, just looked at me and said, "I can't wait to see how you analyze that." And that sort of was the big challenge, to figure out what kind of tools you bring to the table to analyze something that is so chaotic. And so it was really a challenge, but it was a fascinating challenge.
Right, so the flamelets that we're talking about here, just to give people an image, and there are some pictures on the website that are open access if people want to go look, but they kind of look like little fingers kind of propagating along. Can you talk about why that's happening? Is it just because of the low oxygen, that's how it's more efficient for the flame to burn the fuel that's available?
Fletcher, why don't you go on that? Yeah.
Oh, okay, sorry. So, yeah, it seems to be that when you lower the flow velocity and/or the oxygen enough, you start to get these flamelets. So the uniform front can't get enough oxygen, and it's a product sort of the oxygen times the flow rate to continue to maintain its front. So there's little disturbances that cause it to break up into these finger patterns. And Sandra mentioned seeing that, in the Ritzy experiment for the smoldering, but also that was seen by a student, I think it was Lisa Oravez, in the drop tower at NASA, in the 5.2 second drop tower that Sandra mentioned earlier, and she was burning some plexiglass or acrylic, and she saw the same kind of pattern. So we didn't see it in normal gravity, though, until we built the narrow channel apparatus that Indrek has referred to. And with that buoyancy suppression, you see, without the buoyancy suppression, you cannot get to a low enough flow rate to see this, because you have buoyancy that naturally results in a flow of maybe 20 centimeters a second, let's say, of airflow. And you need something like 10 or less in order to see this phenomenon. So you need to either be in microgravity or do something to suppress it, and that's what this narrow channel does.
Right, so the question there is, because buoyancy actually kind of feeds the air into the flame, it's almost like a self-feeding mechanism, that's why the buoyancy is a factor?
It is.
Yes,
a self-feeding mechanism that works very, very nicely under normal conditions that Fletcher was talking about. So like a candle, it generates its own nice flow field that pushes everything upward, so it's drawing the air inward like that. And that's exactly what Fletcher is saying there. And when you can shut that off, which you do in low gravity, then you get these other very interesting things happening.
So one of the things I wanted to go back to is we've talked about drop tests a couple of times here, but we should probably explain why dropping something from a height could simulate a microgravity condition. I don't know who would like to take that one.
Well, given I just did a drop Friday and I'm doing another one on Tuesday, I can talk about it. Basically, when you release something into free fall, and we have a large drop tower here that lets you drop packages in a perfect vacuum, so there's no air drag on the package or anything, and so it's a nice clean experiment to do. But when you drop it and release it and it's just falling at free fall, there's no net force on it. It's falling as fast as gravity is pulling it, and so the effect of gravity goes away for that 5.18 seconds. And during that time is when you can run experiments and get 0 G.
Right, okay. Because
we should also mention that the astronauts that are on the space station that you see behind Sandra are also in a state of free fall. there's really two ways to get to microgravity. One is to be far enough away from a gravitational body like the sun or the Earth that the effect of gravity is very much reduced, but we don't achieve that in the space station or orbiting spacecraft. We're very much affected by Earth's gravity. That's what keeps them in orbit, in fact. And they are, in fact, in a state of free fall. So it's really identical to what's going on when we do a 5-second drop.
Mm-hmm. So
now they're going really fast, and so what's going on is they're constantly falling toward the Earth, but they're also moving perpendicular to the Earth. So they end up going into an orbit, and that's exactly what an orbit is. They're free falling fast enough that they miss the Earth all the time.
Right. Okay, that makes sense.
And over time, you will spiral in, but it takes a long time.
Right. Indrek, maybe you could go back to this narrow channel apparatus that you're talking about. So the limitation of a drop test is you can only do it for 5 seconds. So can you talk about why the narrow channel apparatus kind of mimics the same conditions without that stipulation of dropping?
Yes. What happens in the narrow channel is that, well, there's the narrow channel. It's like that. And if gravity is pointing downward, and the narrow channel is this way, so that the flow is, let's say, from this side coming in, what happens is that because the gap is narrow, you're suppressing buoyant flow, which would want to go upward, so you're suppressing that flow, and so therefore, as far as the physics of the flow field understands it, there is no buoyancy-induced flow, and so therefore it's a, quote, microgravity flow. Well, I don't want to complicate it too quickly here, but the only problem is that since you have a narrow gap, the flame is actually losing heat to the surface above it, and that doesn't happen in real microgravity. But that's just again one of these engineering compromises that you have to face yourself with in doing something like that. So that's the nuts and the bolts of it. You suppress the buoyant flow that would want to normally go upward.
Mm-hmm. That makes sense. Okay. So one of the things I wanted to just get back to here with the flamelets is these, as you've mentioned, a couple of you mentioned, they're somewhat analogous to kind of a smoldering condition in flames, and they can persist in really, really low flow conditions, and that is what makes them so dangerous, I guess, in space. Can you talk about how those might cause problems in a space station kind of environment, if they're, say, in the wiring or something like that?
Fletcher, you're actually...
I'll say something about that. Yeah, so it could occur in wiring or behind panels. It could occur in, clothing. After they've used their clothing, they don't wash it. They'll put it in bags and so forth. And if there could be some ignition source near them, then the flamelets could creep through any flammable material. As Sandra mentioned, there's a lot of flammable material on the space station that has been issued waivers. Clothing is one example, but other things as well. And we screen for a lot of materials and don't allow their use, but other materials there's not a good substitute for them. You couldn't wear metallic clothing, for instance, probably. It wouldn't burn, but it wouldn't be comfortable either. So there's a lot of things on there that could burn, wires and so forth in certain oxygen conditions. And these flamelets they're very dim. They don't move quickly, but they do keep moving. They're kind of pernicious. They're hard to put out. We've tried to blow them out through increasing the velocity in the narrow channel, and really been unable to. They sort of hunker down right on the surface, or even, as Indrek may want to say in a minute, he's studying what happens if they get actually below the surface, and they hide behind part of the surface, and then it's very hard to blow them out, very hard to detect them, and so forth. One thing else that we discovered is they produce a lot of carbon monoxide, which is obviously a very toxic gas, and much more so than a regular flame, and that again goes because they're very oxygen limited. The final product would want to be carbon dioxide, but in the absence of some oxygen, you end up with a lot of carbon monoxide. There's just not enough oxygen.
Can I just, before Fletcher goes on here, can I just interject one little note? If you noticed, he used a couple of biology-based terms there, one of them being pernicious, the other one being hunker down, and the other one being hide. So a lot of these terms are very, very applicable to what we see in these phenomena. phenomena. So
Right.
without even thinking about it, I used.
without even thinking about it, these terms in a way come in.
Yeah.
What the phenomenon is, right?
So there was one very tragic accident that perhaps was due to flamelets, or at least creeping flames, and that was TWA Flight 800 that went down off of Newfoundland in Canada a few years ago. And the Canadians did an incredible job of reconstructing that accident by dredging the seafloor and recovering, I think, close to 90% of the plane, which was. Sorry, my microphone fell down. Excuse
Right.
me.
No problem.
Recovered about 90% of the plane off the ocean floor, put the whole thing back together in a hangar, and then found out that the fire initiated in an entertainment console in the plane and crept behind the panels in the walls, so in a narrow channel in a sense, where there was a little ventilation flow. And it burned through a ventilation line and then got additional oxygen. And it went all this way undetected in above the cockpit, and by the time they did find out there was a fire, it was too late, and the plane went down. So that was an example of something that could happen here on Earth, and we're in a plane. It was similar to what we're studying.
So narrow gaps, wire bundles, things like that, those can be maybe hazard points.
So we're talking here about flames that are very small. There's potentially a lot of fingers, but they're very small individually. They're not producing a lot of smoke, but they're eating through structure at a sort of a steady, if not a fast rate, so they could produce both structural damage without producing any visible signs of what they're doing for an extended period before anybody might notice them.
Mm-hmm.
That's right.
Right. And then you were saying that one of them ate through and got a ventilation line, and so I gather the additional danger here is that if, I think one example that you've given before, and I think this might have happened on Mir, Sandra, let me know if I have this right, where they thought that the fire was out, but in fact it was still kind of doing this flamelet thing, and then when more oxygen reached it, you can get a flare-up before you even realize it.
They did find a smoldering jumpsuit, a uniform, where they had gone to put a fire out, and they thought they had the fire out, and it wasn't until later that they realized that the clothes were still basically had smoldering flamelets going on in them. So yeah, it can happen in space. It didn't flare up in that case, thankfully. They caught it. It could have,
Yeah.
It's a very common occurrence on Earth in real fires, house fires, factory fires, you name it, of there being only smoldering left, and then rushes in a little bit of oxygen, and all of a sudden that smoldering region reignites, as they call it. So that's the reignition phenomenon.
Mm-hmm. Right, and I think one of the things that you have mentioned in your research is that this can also be something that needs to be kept in mind when creating safety protocols for astronauts in space as well, because one of the procedures has been to sort of ventilate the area once the flame is out to get any smoke out of there, but if there's undetected flamelets, that might really cause a disaster.
Yeah, you need to make sure the fire is out, and firefighters on Earth spend a good amount of time making sure all those little smolder spots are out before they leave the fire. And astronauts certainly will have to do a good job of making sure the fire's out.
Now, Fletcher, I think this goes back to what you were saying before about detection. So are there methods that are being worked on to detect flames that are this tiny?
Well, I'm not a detection expert, but thanks for the question. There are the two main methods are to either look for smoke or look for heat. And maybe Sandra can jump in. It's been a little while. I used to work at NASA before I moved to San Diego State. Since I moved to San Diego State, I haven't followed the latest details of fire detection, but there were two types of these sensors there. And the issue with the smoke one I mentioned before was that the soot particles are a lot different sizes in microgravity. And the heat one, of course, if they're burning very much lower temperature than you would expect on Earth or behind something, they'd be harder to detect. So I think in the past, sometimes the best detectors are the crew. They can smell something. If a wire is starting to smolder, they might pick that up faster. So Sandra?
Yeah, they had an event on the mirror. Again, it was on the mirror. They had a failure in their trace contaminant control system, where they had basically purged the carbon bed, and they do that by heating it and dumping it to all the products out of it out to vacuum. Then they switched it back over to air service, but they didn't let it cool. And so what happened is that was hot enough that it started smoldering the carbon in the carbon bed. And that created a lot of CO that was being circulated back into the spacecraft. And fortunately, it created some haze and some smoke. And so even though the smoke detectors never went off on Mir, they had CO levels very high. And fortunately, they caught it and they put oxygen masks on and cleaned it up before anyone was adversely affected. But it was a very dangerous situation because it was this invisible toxic gas and nobody was aware of it.
So is that something that is actually the way that these kinds of fires could be detected? Is it something where a carbon monoxide sensor could be sensitive enough?
Well, the vehicle is very large and mixing is very fast. And so by the time you detect a significant level of CO, you probably have had this fire going on for a while. But it certainly is a marker of low oxygen or low velocity combustion. So it might be a good detector up there. I don't think they currently have a continuously operating the handheld unit that if they smell something, they'll pull it out and then they'll get a reading, but it's not running continuously right now.
So that's still an ongoing area of research, how you might actually detect these sort of undetectable flames.
Right.
Yeah, absolutely.
Right. So one other thing that you kind of alluded to before was how you actually put them out. If they're so persistent, what kind of extreme conditions are required to actually extinguish them?
So there's different types. Sorry, you want to take it, Sandy?
Go ahead, Fletcher.
Oh,
Go ahead.
I was just going to say there's a couple different types of extinguishers on the space stations. I think the Russians have one, and we have one, and there's some other ones that have been under development. So one way is to use something like carbon dioxide that's not exactly a toxic gas. You don't want to breathe a lot of it. You would suffocate, but it doesn't harm you the way carbon monoxide does. But you could blanket the area with carbon dioxide and basically snuff it out because of the lack of oxygen. So that's sort of death by suffocation, if you will. There's also, you can put it out by cooling it, removing the heat from it. And so water is a good way to do that. That's obvious. We do that on Earth, but you can't spray a lot of water around electronics. So there have been some people at the Colorado School of Mines who have been trying to do what's called water mist. Very, very fine mist particles they are liquid, but they're practically a gas, and they don't form, a lot of condensation or liquid water all over whatever you're spraying. The idea of these little tiny droplets, maybe, I don't know if the listeners would appreciate, but maybe 10 micron droplets, which is 1/100 of a millimeter in diameter. So very small. And they will absorb heat when they evaporate and sort of cool down. So,
I imagine they're pretty efficient evaporation too at that scale.
yes, exactly, because of the large surface area. Exactly right. Yeah. But I don't think that's been approved for use yet. That was, last I understood, that was still undergoing testing. Sandra may have some more up-to-date info.
I think they're planning on replacing half of the CO2 cylinders with water mist, but I might be wrong about that. But I do believe they're planning on flying some.
All right. Sandra, did you have any other things to add to what Fletcher was saying before about ways of extinguishing these flames?
Who, me? No.
Well, one thing I always think is a great idea, and I mean, they sort of did it on the Mir with their jumpsuit, their clothing, is to use a fire blanket. Fire blanket technology is old, but the nice thing about a fire blanket is it literally just stops the oxygen from getting to the fire zone and encapsulates the flame so it can't continue to spread out. It's a very low tech, doesn't have any really moving parts. The only trick is how you deploy it in space, and that would be something that would have to be tested. And could you safely deploy a fire blanket? I was picturing something like a not an umbrella, but some kind of a mechanism that you could be somewhat far back from the fire and still manage to get it to cover the fire.
Right. Okay.
Another concept that people have looked at least theoretically, is evacuating the particular module where the fire might be. But that has a lot of potential pitfalls in that, we talked about rushing air causing the fire to grow larger, and when you open, say you were able to quickly isolate a module, get the people out, seal it off, and open some kind of hatch, initially that would create a lot of maybe violent airflow that would cause the fire to become much worse than it otherwise would have. And then, you'd have to go through a whole repressurization process. But I think in a very last-ditch effort, that is a possibility.
So, Indrek, when you're looking at these narrow channel apparatus, I know one of the things you're talking about was heat transfer. Did you develop, I wonder if you talk about some of your research in that area with heat transfer and extinguishing these flames, because I think that's something that you've also looked at.
Well, I mean, in the narrow channel, the thing is that the physics of the problem are different. And so you do have that upper wall, and there is heat transfer to it, and that does change the problem a little bit. So basically, I mean, we haven't really researched the full problem of the heat transfer, but we have, over the years, done enough work to determine that there seems to be an optimal gap width that does a decent job of simulating the microgravity while not overwhelming the problem with too much heat loss. If you go to too narrow a gap, the heat loss essentially kills off the flame. If you go to too wide a gap, then you have, again, the influences of gravity, because now the flow can go vertically again.
Mm-hmm.
So we found, at least for the kind of tests that we're doing, something of the order of 5 millimeters is pretty good. If you go down to 2.5 or 3 millimeters, then the gaps are too close almost, and then that kills off the flame. If the gap is 10 millimeters, 11, 12 millimeters or so, then now the flow has enough room to go upward, and so it's distorted by gravity. So far in our work, 5 millimeter-ish would be a norm that would seem to work, and that affects a nice compromise between all of the physics that are there.
Yeah, I think there's been at least some trial and error in the development of the exact channel that you need in order to simulate the conditions.
Right. There's been a lot of trial and error, and we had some students who just varied the gap, just quite frankly, and what do? You look at it and see if it resembles a microgravity a flame, the one that you have in the drop tower. And if it does, then you press on, and if it doesn't, then maybe either you narrow the gap or you make it bigger. And so there was a lot of trial and error, and I was very lucky to have some very good students who worked on that problem.
Mm-hmm.
Yeah, so if you're measuring the flame spread rate and you're varying the flow, what happens is if you start at a high velocity and you start reducing the airflow velocity, the flame actually gets faster, because there's I like to call it the Goldilocks zone of flow. It's like you're just giving it the right amount of oxygen, but you're not blowing too hard to cool it. And so what happens is as you reduce your velocity, the flame initially accelerates and gets faster. But then once you keep cutting the velocity, it starts starving. And then it slows back down. So there's that peak in how fast the flame velocity is only really accessible in a spacecraft due to the ventilation systems. So, and the ventilation systems are designed to provide that amount of velocity on average. So spacecraft design and flammability are not playing very well together at this point.
Right. So the reason why the flame speeds up, if I can conjecture here, is that got to do with the fact that it's just got more time to consume the fuel that's there?
Yeah, it's basically, it's got enough oxygen still. And heating excessive amounts of air, because the faster the air flows, the more the flame has to heat more of that air, because it's kind of like just like, I don't know what a good example would be, but you just have to heat more air if the air is flowing faster. And in that case, it's sort of a heat loss, just like Indrek was talking about heat loss to the walls. This higher velocity air is a heat loss because you have to heat more air. And so if you reduce the airflow for some period of time, over some range of velocity, the flame will actually accelerate. And there's a peak in the spread rate the flame spread rate at a velocity of about 10 or 15 centimeters a second. And that's lower than you get on Earth.
Right, okay. So just to go back to some of the BAS experiments for a second here, in terms of the materials that you're testing, you're saying that part of the point of the experiment was to sort of do flammability tests for materials that are going into space, but you're in the first BAS mission, if I remember correctly, I think you were using actual candles, and in the second one you're using sort of acrylic rods to simulate those. And I think people might be a little surprised to hear how flammable acrylic is. I wondered if you could kind of talk about the materials that you're actually using and sort of their flammability factor, and if there's something different about those conditions that actually changes how flammable things are.
Well, in BAS 1 we used actually 2 different kinds of wax candles. They were wax. They were encapsulated in a little ceramic sleeve so that they didn't break off or get on the astronauts' hands, but it was actually wax, paraffin. Acrylic, as you indicated, that's called polymethyl methacrylate, is the chemical name of it. We call it PMMA for short. But it's basically acrylic, and a lot of stuff is made out of acrylic. Unfortunately, acrylic is extremely flammable in air. And so I've seen a lot of things that you might think it's glass, and so it's like a little candle holder with these little glass crystal things, but those are actually acrylic. And so you're setting a fire inside of a very flammable decorative piece, so don't do that. It's a real concern. One of the problems that I think we have with acrylic is that it's very lightweight and transparent, and so commercial spacecraft want to use it as their windows, and they're thick windows and they're multi-layered. But it's a concern because if you had an ignition source that was adequate enough to ignite the window would be flammable in the spacecraft. Fortunately, they're keeping all the ignition sources away from the windows so they don't burn.
Correct me if I'm wrong, but don't they use acrylic in, let's say, the bulletproof windows when you go to one of these establishments, maybe a bank nowadays? They have those very, very thick windows sometimes. Those are acrylic, aren't they?
I think so, yeah.
It will stop a bullet.
They're not.
Very good dynamic properties, but they have thermal properties that aren't too great. It's again one of those engineering trade-offs that you have.
Wait, no, I gotta correct you. I think the bank bulletproof transparent windows are polycarbonate, not acrylic.
Polycarbonate.
Oh.
Okay.
Yeah, they're polycarbonate. Yeah.
So,
Which also is flammable, but not as flammable nearly as acrylic.
so polycarbonate, would that be plexiglass or?
That's Lexan.
Lexan is a trade name for it, or Tufac
Yeah.
is another one. But yeah, so acrylic and polycarbonate are not the same type of plastic.
Mm-hmm.
Well, I know
The other reason we use PMMA or acrylic is it's a kind of an ideal fuel for combustion studies. It burns away without leaving charge significantly, so we keep its shape and cause other problems. So it's an idealized fuel, which is why we have used it a lot. When we're trying to understand the benefits, you don't want these confounding factors of cracking fuels and residues that are building up and things like that. So it's very nice for that purposes.
Right, okay, that makes sense. We actually only have about 5 minutes left here, so I'm hoping we can kind of do things, a few things that are a little more forward-looking now. I'm sure you've got some upcoming tests and missions that are planned. I wondered if you guys could talk about those for a few minutes.
Sandy, why don't you lead off? You're the NASA contact.
Okay, well, we mentioned earlier about the Sophie experiment, the solid fuel ignition and extinction experiment. There are 5 PIs for that. And we're building a specific insert to go into a space station rack called the combustion integrated rack. And our insert will allow us to provide a larger scale flow duct to run these experiments. And that will allow us longer times of high quality burning, so you can get spread rates or flame spread over a longer, larger sample. Some of the BAS experiments ran for a half an hour. And so we're expecting to get even longer experiments than that in the Sophie insert.
So just to clarify here, The small apparatus was what was previously referred to, I think, as the glove box. Is that right, Sandy? And now the larger one
The
is
bass.
the IR.
Yeah.
Yeah.
Yeah, SIR is the chamber that it would be in, but our insert would be a larger duct.
Okay.
So in the Sophie experiment, one of the key things that's important for our particular experiment is going to be the ability to vary the pressure as well as the oxygen concentration going up above normal atmospheric or Earth oxygen concentration to 21%. New spacecraft environments, NASA's trying to move to higher oxygen, lower pressure for some both crew physiological reasons and other reasons too. There's a lot of reasons, in fact, to go to high oxygen, low pressure. Apollo was the ultimate in that. It was 100% oxygen and very low pressure. NASA doesn't want to go to that extreme, but there's a lot of reasons to go to the high oxygen, low pressure, but that really changes the findability. So in the Sophie experiments, we're going to be testing that in our particular tests and comparing to our narrow channel results. And we couldn't do that in the Bass experiments because the glove box can't vary the pressure and can't go above 21% oxygen. So one other thing I'll just throw out there as far as future, I think coming up this year is going to be, none of us are directly involved, but NASA's some other people that work with Sandra. NASA's going to be conducting what's called, or what we call the Big Burn, which is going to be a very large sample of, in fact, different samples of materials in a Russian spacecraft that's going to deorbit from the space station and then burn some samples, I think up to a half a meter or a meter long, Sandra, something like that. So you could never do that on a manned space vehicle or a crewed space vehicle. But this is an unmanned vehicle designed to come back to Earth and burn up in the atmosphere. And so there's going to be something akin to a bigger fire on board that it's going to be videotaped and then downlink telemetry. Of course, everything will burn up, the spacecraft included, but they want to get the data from it before that happens. So, yeah, you might have a few more details.
Yeah, the first launch of that is in March, and but obviously it stays docked to the space station for a while before undocks. So after it undocks, it'll be in May. And so we'll actually run the experiment, after undocked in May before it burns up. So we're very excited about it. That experiment's called Sapphire, actually. Safety of fires is what it means, but it's called Sapphire, and it's launching in March.
Yeah, those will be the biggest flames, other than the Mir fire, I think, which was uncontrolled and unplanned. Biggest flames ever in space. So that's going to be exciting.
I'm glad to hear these ones will be controlled at least.
Well,
hopefully, right?
The point is, if they get out of control, it doesn't matter so much.
Right.
Just a parenthetic note: in the movie The Martian, the main character, Damon, I guess, what's his name? Matt Damon. His goal was to try to develop water on Mars so he could water his potatoes. And he was all upset that, and he made the comment that NASA just sends up so many of these non-flammable materials that he had nothing to burn. So he was upset by that. That was a pretty clever twist on all of NASA's fire research. Somebody had to know that.
Right. Yeah. I guess he was paying attention to the research.
Somebody was paying attention. A screenwriter.
Right. Okay, great. Okay, so we're actually out of time, so I'm going to thank our guests again. We've got Sandra Olson at NASA Glenn Research Center, Fletcher Miller at San Diego State University, Indrek Wichman at Michigan State University. Their article on flamelets and fire in microgravity is currently in the current issue of American Scientist. It's open access on our website. Please check back for a slideshow of related images to the BASS mission, which Sandra was talking about. And thanks very much for watching. We'll see you next time.
Thank you.
Thank you.
Thank you.